Now it is time to revisit the idea of activation energy. If you go back to imagining the microscopic scale on which reactions actually occur, we discussed all of the different things that must happen in order for reactants to interact favorably towards yielding a product. For example, we discussed how the bonds and intermolecular forces which hold reactants together as molecules must be broken. All of these initial steps require some energy. This energy is called activation energy. You can see this illustrated in the reaction coordinate diagram, in which the y-axis is energy and the x-axis is the progress of the reaction. At the beginning of the reaction, you will see the reactants which, when supplied with enough energy, make it to the top of the curve to this point, which is called the transition state. At this point, they could either reform the reactants or proceed to the products. This concept works as an explanation as to why increasing the energy of a system increases the reaction rate. By raising the temperature, you increase the reaction rate by increasing the number of molecules in that system that have enough energy to overcome this activation energy barrier. All right, do you remember the collision theory we discussed previously? It stated that a reaction cannot occur unless the molecules collide with enough energy and in the right orientation. There is an equation which allows us to study the effects of these variables against the rate constant. If you think about it, the lower the probability of achieving the correct geometry, that correct alignment, the fewer the collisions. That's going to cause a lower rate. And if you have a lower rate, you're going to have a smaller rate constant that applies to that set of reactants at that temperature. The equation that connects these is called the Arrhenius equation. And it looks like this here at the top. In this equation, K is the rate constant, R is the gas constant, T is the temperature, and A is something called the frequency factor. And the frequency factor is particular to a specific reaction at a given temperature. This variable in the Arrhenius equation, the E with the exponent, refers to the number of molecules having the amount of energy for a reaction. Its value is always less than 1. A couple of things that this equation can be used for is to calculate the activation energy of a reaction, but it can also be used to calculate the value for any of the variables in the equation, including rate constant. Okay. This equation comes in several forms. The first form is the normal form that we have written up above already. The second form is the natural log form, which looks like this.